Good morning, everyone. Thank you for joining us for this first grand round of the year. I'm going to ask Dr. Sarah Williams, our faculty host this morning, to introduce our speaker. Thank you for joining us.
Thank you, Amy. Good morning. I have the great pleasure of introducing Dr. Hooman Rashidi as today's grand round speaker, who is joining us from UC Davis. Professor Rashidi has been with the Department of Pathology and Laboratory Medicine at UC Davis since 2014, where he is a professor and vice chair of graduate medical education, vice chair of informatics and computational pathology, director of flow cytometry and immunology, and director of the residency program. He completed his APCP training at Yale and his hematopathology fellowship at UCLA. Using his background in computer programming, Dr. Rashidi developed hematology outlines and Heme Quiz 1, both innovative apps and teaching tools endorsed by the ASCP. I encourage all of our trainees to download both. You will not regret it. Dr. Rashidi's unique background in computer programming and bioinformatics has also enabled him to develop novel artificial intelligence and machine learning platforms, including the one he'll be sharing and teaching us about today. Machine Intelligence Learning Optimizer has led to multiple clinical, educational, and quality improvement projects. Please join me in welcoming Dr. Hooman Rashidi.
Well, thank you for the kind invite and the very kind intro. And I hope you enjoy this talk. So hopefully you can hear me right now, okay, right?
Yes.
And you can see. Terrific. Well, without further ado, let me get started. Let me just click that. So as was nicely mentioned, my background, I'm a practicing physician still. I'm still a boarded hematopathologist. I'm actually on service still. And my background was bioinformatics, as was mentioned, hence the interest and the need to wanting to do this within our platform, especially in pathology and laboratory medicine. I'm not putting my books out here for you to go buy, but this is just to show that the thing that I'm going to show you later on was, was basically a way for us to use my background and my core group's background, and along with 30 plus people that are within my research group, to see how we can actually optimize this platform. And that's where MILO was born from. But before talking about MILO, I need to make some disclosures. The things that I'm going to show you, they're based on 3 intellectual properties of the University of California, including MILO, which I'm a co-inventor of. And so I've made that disclosure, as you can see here. In terms of the outline of the talk, I'm going to be talking about machine learning overview. So I apologize for those of you who actually have a background in machine learning, that I'm actually repeating some of the stuff that's common to you. But I think most people don't know about some of the basics of machine learning. So I will go through that so you can appreciate as we go through it. Besides that, since supervised machine learning is by far the most common machine learning platform that everybody uses, especially within our fields in medicine, I will go through that and at least touch base on it. For more details, I recommend reading one of our review papers, which goes into a lot more detail. It's almost like a mini chapter in academic pathology, which I think was forwarded to everybody. And then specifically within supervised machine learning, I'm going to be talking about this concept of study design, specifically the modified CRISP-BM, which is IBM's modified approach in terms of doing best practices within machine learning. And then pretty much every supervised machine learning follows this concept of bias and variance trade-off. And so I'm going to kind of go over that, just touch on it so you understand when somebody says bias and variance, what do they mean? And how does that apply to machine learning? And then finally, how does it apply to actual studies? So I'll show you one of our studies within our Burns population, which that's one of them that turned into its own patent pending application, which was our acute kidney injury machine learning study, which has its own optimized machine learning model now. And then finally, can all of these things be automated? And the answer is yes. And I'll show you our newest automated machine learning platform called MILO. And so not making any assumptions, there's people who talk about artificial intelligence, machine learning. Just to kind of like clarify this, machine learning is just a niche within artificial intelligence. And so it can be interchangeably used. Specifically, like one of the fathers of machine learning, artificial intelligence, Arthur Samuel, coined the phrase that it's a way that they computers or systems can automatically learn from experience without explicit programming. That's semi-true, just to be fair, because reality is those of us who do this, we know that when we're building these things, there is programming involved. But the concept is that once you've made the programming and made the blueprint, that the computer can actually do a lot of things automatically because of what it's learned. And there's a lot of similarity between machine learning and human learning. In human learning, you're learning from experiences, touch, feel, see, that sort of thing, sight. Versus in machine learning, you're basically getting the same stuff, but through data. So the computer basically learns, or the program learns from data. So some examples of AI and ML, if you're one of those folks who basically, and I've definitely had nice conversations with them, and that they feel like they don't need AI ML and they don't use it in their daily life, I think you're mistaken, because if you use an email, you use AI ML. And if you have an iPhone or an Android, you definitely use them with Siri. And spam filtering is what I meant, is that if you use an email, if you notice that some of your stuff stays in spam and some of them we call ham, so bad email, good email, that classification scheme is the classic machine learning platform that's embedded within your system. So you are using it, even if you don't, if you didn't think you were. But obviously, if you're at home and using Amazon, to shop something, or Netflix to get, different movies and recommendations and stuff like that, those are all machine learning platforms that are actually doing that for you. But then the main question is there a difference between machine learning for things like Netflix versus within the medical applications? And the answer is absolutely. There's a huge difference between it. And the main difference is that, as you know, the practice of medicine, as much as we want to say that it's 100% a science, it really is still not a science. It's still a balance between art and science. As you know, it's very much experience driven, especially we know this within our own field, where you have somebody who's got 10 plus years experience. They basically can make a call on something and see subtleties that you just basically acquire over time. And then the other thing is that within the practice of medicine, pathology and other aspects of medicine, there is always this inter-observer variability. So if you basically, depends to what field of medicine you're talking about, that inter-observer variability, even for experts, could be great. So we heard about a talk not too long ago where the speaker was from critical care, and within the critical care, they were saying that between their experts, they could be off by as much as 40%. And so obviously in pathology, we're not off that much, but still, so it depends what kind of a field you're talking about. So minimizing this inter-observer variability is key to making sure that your data is reproducible. So having initially data that's vetted and can actually be reproduced between experts is a key concept before you can start any kind of a machine learning process, because otherwise, if you don't, you're not going to get good results and good models. But so the main question is that what machine learning approaches are used in most things in medicine and pathology, as I described earlier, that's the supervised machine learning. And just to kind of like bring everybody on the same page, what I mean by supervised machine learning, typically machine learning is split, the way we typically split them is into these three camps: reinforcement learning, unsupervised learning, and supervised learning. Reinforcement learning, I'm not going to go into, or even unsupervised learning, I'm not going to go into too much. You can read the papers on those. But those reinforcement learning is basically when you have an automated robot, let's say an automated dog that learns what's the fastest route to a corner of a room and just learns with time, Unsupervised is where, as the name implies, the user basically is not putting any of their expert input into it. It tries to find clusters or do dimensionality reduction, like PCA. And And so that we commonly use the unsupervised platforms to actually feed into supervised platforms. But ultimately, when we're building models, we're typically, within our field, we're typically using supervised platforms. And then the supervised platforms, the vast majority of the stuff that we actually build are in the classification scheme. So that's like cancer, no cancer, acute kidney injury, no acute kidney injury, or sepsis, no sepsis. Regression supervised models are more numerical outputs. So let's say if you're in real estate and you buy a house and you want to figure out, this new house that has 5 bedrooms and, 3 baths and it's in this zip code, it can predict based on other things it's learned, this is the price range that it should be, versus an actual discrete qualitative output, which we see in classification. Most of the things that I'm going to concentrate on today will be on classification schemes, since that's the vast majority of stuff we deal with within medicine and within pathology. But when you're talking about classification scheme, there could be many different algorithms that could be used. So you've heard about neural networks and deep learning, that's, when they use neural networks, specifically convolutional neural networks. But there's lots of other algorithms that we actually use and have been around that could be just as useful. And so, but many people are not comfortable diving into it. Even in this paper, we've removed most of the math, and it's just a new concept to many people. But I'm encouraging people to kind of getting comfortable with this, because, quite frank, I personally think within pathology and laboratory medicine, especially, we should try to keep ownership of this, so that just the quality that we actually convey within these models basically are representative, just like when we're developing laboratory tests, which we are most familiar with within the medical field than our colleagues who are outside of laboratory medicine and pathology. So that's my biggest pitch, is that for us to keep ownership of this world for patient care reasons, because we want to make sure the quality of these platforms that are coming out are keeping up with the same qualities that we assess when we're developing laboratory tests. In AI and healthcare, really, the way to develop them, and if you're asking yourself where to start, you can kind of like split them up into like a quick little 4-step process in terms of where to start. Obviously, everything starts with data. So you want to initially have good data, evaluated the accessibility and the quality of the data, and making sure it's complete as possible, making sure that the data is reproducible or generalizable once you put in unknowns in it, so it actually matches real world stuff. But obviously, a lot of times you may have to start with research material that then it gets conveyed into real world material. Exactly what does that mean within the classic gold standard study design approach? This is the study design approach, is the modified IBM's cross-industry standard protocol for data mining, which basically follows these steps. And the steps have the initial steps, which is the date involving the data before you even do any machine learning. And that involves actually taking on your data and then using your data, making sure that you're getting rid of the missing data, scaling it. And then you could also even sometimes put in, selecting the right features, so doing some unsupervised platforms before you feed it into the supervised process. Ultimately, in the CRISP-DM approach, once you build the data, then you basically can go into the yellow area, which is where you do the supervised platform. And then finally, when you build the supervised models, then if they're actually delivering what you're looking for and they're actually performing as you expect, then you can deploy them. Ultimately, the reason you want to do this is because if you don't put in the right data, it's the whole concept of garbage in, garbage out. So if the data is basically no good, or may exaggerate certain things, or may not actually represent the final target and not correlate with cancer or acute kidney injury or whatnot, then it's not going to actually be useful in terms of the model itself. So it's not going to give you a generalizable model ultimately. So that's a very important concept for me. So ultimately, regardless of what kind of a great machine learning platform you have and what kind of algorithms you use, it's very important for you to start off with really good data and start off the foot right on the right path, because otherwise you're not going to get on the right model. Ultimately, at that point, assuming that you've gotten the right data, at this point, you start basically planning to build the data. And that's basically optimizing and getting the optimal machine learning models. In basically all of the supervised machine learning models, they share this one common step, and that is a training and a testing step. And what that means is that the data set is, simply put, is a subset of it is taken off as a training set. And so let's say 80% of it is taken out to be training for the model, and the model gets trained and internally validated, and then you leave some of it out, and that ends up, let's say 20% of it, and that ends up testing the model to say, okay, the things that I trained, the models that I've built with that 80% of the data, let me see how well they do on that 20% that I left out. And obviously you would want to repeat that process and, you know, do cross-validation so that it's statistically significant. But ultimately there's this training and testing step. And within this CRISP-DM approach that I was just showing you, this is where the training and testing comes in, where the data basically gets split into the training and testing. And within the training data set, you build the models with the different algorithms, and then that test set validates those models. And then even better so, if you really want to do really good studies, you don't want to depend on that just test set. You want to bring in a secondary data set, because if you build it with just that initial test set, you might be overfitting models and they may not actually be generalizable to real world material. So bringing in a secondary data set, preferably that's actually representative of the true prevalence, and testing it on the models that you've built will give you a better indication if you're dealing with the right model and a generalizable model. And then ultimately, or if you're happy with that model, then you can deploy it. So that's this yellow area represents what you do in supervised learning. But within that supervised learning, how do you know which model ends up being the best model for you to test on unknown stuff? And the way that people try to do this is finding this balance between bias and variance. And simply put, this is basically saying finding the balance of, you know, between overtraining and undertraining a model. If you overtrain a model too much, you're typically overfitting. If you undertrain it, you're typically underfitting. So in order for you to be able to figure out where you're at in terms of where the best model is, you have to find out where that best bias variance trade-off spot is for that model. And exactly what does that mean? What that means is the following, is that imagine you have, to optimize your model, you actually start off training your model with this training phase. And as you train the model with model complexity, so the more connections the data is made to the target, you find out that the error drops. So you end up with a better model there. Ultimately, that's not the model because you haven't tested it. And once you test it with that orange line, you find out that at some point, the best lowest error rate happens to be right here at this bottom area. And so, and when do you do this? Because that happens to be where you end up having you bring in the variance as much as possible, and you basically try to get the best model fitted at that point. Because if you're below that line, you'll be getting underfitted models, versus if you're above that orange line, you would be getting overfitted models. So really the range of where the best model is that right there in that low area, which basically we call it the bias variance trade-off model. But ultimately, that's not even the best area, because within that, you actually still have lots of areas to actually test out. And even though this is the lowest area here, the best area within this range here may actually be something to the left or something to the right. So you really should be testing it on a secondary data set as well, so that, and even preferably even a tertiary data set even after that, so to see truly where the actual generalizable model is. And if you noticed, if you did it here in this case, a secondary data that basically is tested on that same model finds it that it's actually to the left of that low peak in terms of the error. And the most generalizable model happens to be the one based on that secondary test set, or even better so tertiary test set later on, than that initial first test set that you've tested out. Ultimately, you do this because you want to minimize this very popular concept, but a known fact within our world, which is overfitting. And put it simply in terms of the actual data. So if you noticed right here, if you don't make enough connections between the data sets, these are 3 identical data sets. If you don't make enough connections and you draw a straight line, you notice that there's not enough actual things learned from the line, the function. And so you're underfitting in terms of an actual model. So it's not going to be able to predict really well because it's underfitted. If you make too many connections between the data set, then if you put in an unknown right there, the likelihood is that it's not going to be within the wiggly lines or that wiggly function. So it's not going to do well because it's overfitted. And then finally, maybe a hyperbolic function curve might fit in best, and a lot of times that's the case. And so that ends up being your best fitted model. And that's what we mean when we say the balance between bias and variance, so that you can ultimately find the best fitted model that minimizes the overfitting phenomenon is the most generalizable. You do all of this because you're assessing the generalizability of the models itself so that it can actually perform for real world data ultimately. And obviously the model assessments are done with classic statistical, parameters that you are familiar with like accuracy, precision, which is another name for positive predictive value, ROC, AUC, sensitivity, specificity, F1 score, or if you want to look and see how well they do it in terms of its probability itself, you can do a Breyer score. And these are different parameters that you can do within machine learning world, but I'm sure you've heard about most of these things. But ultimately, even if you built a model that you feel like it's doing a great job, if it doesn't address a need, it's not going to be worth anything. As the real world, as it says here, could be a tough place. So this was the MD Anderson, IBM Watson experiment that I'm sure most of you had heard about, that was in the news a few years back. And as the newspaper basically talks about, as they were building this oncology expert advisor for target cancer therapy, because even though this was a fantastic team and a fantastic setup and a great idea, because they were not really meeting a need within the niche that they were looking for, it ultimately didn't do well. So it ultimately, had $62 million, according to this author, wasted without achieving the ultimate goals. But that being said, hopefully this was a learning experience for them, and they're moving forward with better and bigger things. But ultimately, the process, even if you have a fantastic team, the process could be actually a very difficult one to tap into with machine learning and medicine, because there's lots of subtle things within medicine, the way we practice medicine, and it's not as easy as things outside of the medical field. So our view of it is, because of that, it might be best and safest if we actually approach machine learning platforms within healthcare and go after the lowest hanging fruit, really. And what I mean by lowest hanging fruit is things like an acute kidney injury model, for example, as I'll show you here. So our goal here was to build a machine learning platform where it could predict acute kidney injury within the machine learning platform, because right now the gold standard for identifying acute kidney injury doesn't do a great job. And what I mean by that is the gold standard is this thing called KDIGO, which is kidney disease and improving global outcome. And KDIGO is based on serial creatinine and urine outputs, in short. And so because it's serial creatinine and urine outputs, it takes days for you to potentially get the answer. And even with that, not surprisingly, because urine output especially can be very variable, it doesn't have the best sensitivity, especially within the population we were looking at, which was Burns population. And so the question was, can we improve this with machine learning? And we were kind of lucky because our Met Center had the clinical trials for NGAL, which is this new biomarker that without machine learning. So this was a biomarker that is now used in Europe, and it definitely outperforms the KDIGO, and it does much better performance than the sensitivities of 50s. It's like more in the high 70s, low 80s. And our question was, can we improve that even further? And the reason for that was because if you don't even do machine learning, so this is no machine learning, just to split up where the acute kidney injury patients versus no acute kidney injury patients lie within these biomarkers. If you notice with creatinine, you have some variability, urine output, you have a bunch of variability, and BNP, not as much variability, and that's for the cardiorenal function that you see with acute kidney injury. But NGAL looks pretty clean, but it still has some negative no AKI cases built in it. So by itself, as a statistical modeling approach, it may not be the best approach because you still will miss certain people. And so it may not have the best performance. It definitely outperforms the KDIGO, but it can definitely has room for improvement, as we've seen here. So our goal here was to see, can we use machine learning? And we actually found one of the most simplest models, the KNN, the K-nearest neighbor model, could actually enhance NGAL's performance. And it was able to enhance it by combining it with other biomarkers like BNP, creatinine, and urine output. And by doing that, we were able to actually bring the sensitivity and accuracies in the low 90s. And so that was a huge bump. So imagine you're going from a KDIGO in the 50s to an NGAL, which can get you into the high 70s, and now you're going into the low 90s. So clearly there's a role for machine learning in terms of enhancing this process. Our follow-up studies showed the same thing, that actually was exciting because our models were actually able to perform even outside of the burns population. So the non-burn trauma patient population also did really well when we actually looked at our acute kidney injury prediction. And this is basically showing that there were different algorithms that were found that did really well, including a neural network. Ultimately, this is what we're finding, is that if you use creatinine by itself, and here's the ROC curves for the different algorithms that are used. So neural network, logistic regression, KNN, whatnot. And if you notice that it's not doing so well when you're looking at creatinine and urine output, obviously creatinine alone and urine output alone, they don't do well at all in terms of the ROC AUC. When you combine them, they do slightly better, but still not good. And that kind of explains the 50%, the 50s sensitivities that you see. So that kind of matches the literature. So when you introduce NGAL, actually, you all of a sudden, with machine learning, you all of a sudden see a gigantic bump in terms of their performance. Long story short, you notice that with the NGAL and with the other biomarkers combined, this one had no urine output in the top left. You see that you have a much better performance, and now you're in the 90s in terms of the performance. So in summary, the acute kidney injury model trained on the burn population were able to predict acute kidney injury in non-burn trauma and burn populations with much enhanced performances than previously seen. And the machine learning, so it clearly enhanced the predictive capability of NGAL, and NGAL combined with other biomarkers, specifically creatinine and BNP. Most importantly, the reason we actually got an IP for this machine learning process was because we were able to do all of these with admission data. So instead of waiting for serial values of creatinine, NGAL, or even be a UOP, we were actually able to do it with admission data, and the admission data was able to predict the future in terms of what's going to happen to the patient, in terms of if they're going to develop AKI or not, or are they in the early stages of AKI or not. And that was able to do it by, it actually decreased the time close to 2 days. So that's a huge step. So because this is something that you could potentially use as a point of care device and even do in outpatient settings, be able to identify patients. And we have multiple additional studies that are coming from this, because this is actually in its 3rd stage of clinical trials now. This is what I meant in terms of how well it actually can do it. So if you did without NGAL, you notice that, and you did the KDIGO approach, you're going to find out that you have to take several days for you to get the answer. And when you actually improve it with NGAL and with machine learning, you actually cut the time down quite a bit and get the answer much faster, and potentially can intervene if it's in the proper settings. So now the main question that some of you may be asking is, can this machine learning process that I showed you, can this be automated? let's say you don't have a background in machine learning, but you really have a fantastic idea and you want to be able to test your idea because you found a great thing that you could test and potentially could change the way patients are managed. And the answer is, how do you automate this thing if you have no background in machine learning and if you don't know how to program or you have no software engineering expertise to build web apps? So can you still tap into this world and start using it? And the answer is absolutely. You can do it, and our automated approach allows for this. And we call it MILO, which is Machine Intelligence Learning Optimizer. To be fully transparent, what I'm going to show you, this is only for non-image classifications. So it's an automated machine learning, it's an optimized automated machine learning platform for non-image classifications. Means that if you have an image and you want to do classifications, this is not going to be able to help you out with it. So this is optimized only for things like laboratory values, clinical, physical exam, scores, that sort of thing. So, and so that's just something to keep in mind. The reason you want to do this, as I was showing you, is because increasingly the number of uses of machine learning platforms are increasing within our world, and they're actually not going to go anywhere. They're increasing with each day. So instead of kind of like resisting, I think it's best if people start understanding this and become part of the process. And the automated machine learning platforms are going to be very useful because you can kind of think about them. Before Microsoft Excel came about, people were doing a lot of those things manually, but now with Microsoft Excel, you can do a lot of complicated calculations within Excel, but you don't have to have any coding background and any programming background. You just use Excel's embedded platforms. So similar idea here, where you're using a lot of the embedded stuff within the machine learning process and statistical approaches and building tools, all within a platform that's automated, and you as the user just bring in your great idea, and then you let your great idea find the right models if you could find them. And if you don't find them, then you start looking and reassessing the study design and find ultimately until you find the best model that are basically going to help you out for whatever process you're interested in. But there are some major challenges within this machine learning process. Even though people want to do machine learning, as I was saying earlier, one of the biggest issues is that it's intimidating. So a lot of people who don't have machine learning background, or they're not statisticians or having programming expertise, they don't want to get into this platform or get into this realm because they have to learn something new. And so that's one of its biggest challenges that I see. The other one that I see a lot is that it's very time consuming. Most of us have full-time jobs, and when we even have a great idea, we don't want to tap into this because we know it's going to basically be very time consuming, having to build a team to basically be able to do machine learning. It could take months to a year to kind of even build a model once you get the right people in the same place. So saving time is a huge part of the process, since most of us in this world actually have other clinical duties, and our research duties are complementing our clinical duties, but they're not the primary source typically. And then finally, this one I see a lot. I review AI/ML articles pretty much every week, and so I see some fantastic models that are being built and published, but unfortunately, probably 99% of them, or at least the vast majority, they're not becoming products. So they're staying in literature. So they just are built, they're published, and they stayed in literature, and nobody ever uses them in the future. And obviously there's multiple reasons for that. There's obviously medical legal reasons, but the other big reason is the idea of resources, that maybe there is the people don't have the right skill sets to be able to convert a model that they've built in one language, which is typically Python, and convert it to another language, which for a web app, let's say, that you need to know HTML2, CSS, that sort of thing. And so it would be great, wouldn't it be great if you can imagine a world where you can do AI/ML studies, and it could become as easy as using a website on your laptop or even your smartphone on your iPhone or Android device, where there will be no need for machine learning expertise. You don't have to be an expert statistician. You just need to know some statistics, of course. And then there'll be no software engineering expertise needed, no programming required. It will be just easy to do. And our solution was MILO to this. And MILO allows any investigator to have accessibility to machine learning platforms without having any background in coding, programming, or machine learning expertise. So all the heavy lifting is done by MILO. Its key highlights are it expedites the machine learning process, and I'll show you the data on that in terms of how much it does that. So it's much, much faster than a non-automated approach. It actually outperforms the non-automated approach, as we've shown it and others have, in terms of how it works. And once I show you how it works, it becomes common sense why it outperforms it. And then final thing that I feel is very important is that it has a very user-friendly interface so that anybody can do the studies, but also just as importantly, anybody can show it to others in a very easy to understand platform, because it doesn't have codes to show people. So then it's easy for one person to show somebody else just the idea rather than getting into how the models were built. So the proper user interface is very important. What I meant by expediting the process, again, these are the separate IPs that I was mentioning earlier. So our acute kidney injury, as I showed you in the study, that took us 4 months of nonstop work to find the optimized ML model. MILO was able to do and find the best model, actually found a slightly better model, and it did it in less than a day. So something that took us 4 months, MILO did less than a day. Same thing with sepsis, something that took us 3 to 4 months, and here NAM says 3 months, but it's really 4 months. So 3 to 4 months in finding the best model to identify sepsis, and MILO was able to find it also in less than a day. And by the way, we're seeing this over and over with all the other data sets we have too. So it's just so much faster than doing the non-automated approach. Most importantly, MILO's platform is a validated platform, as we've published on. There's multiple other papers that are actually accepted and coming out soon too. And I say over here, validated on 10 different IRB approved studies. It's actually 11 now, and by the end of the year, hopefully it'll be like 17. And if you notice right here, they're in different fields in medicine. So some of our studies are within acute kidney injury, within burn patients or burn surgery, trauma surgery. Some of them are in kidney transplant world. Some of them are in cardiology. Some of them are in infectious disease, or even in transfusion medicine. But if you notice, the last two have nothing to do with medicine. We have models that are also that are built to predict if the students are going to do well on USMLE or not. And by the way, this is not a theory that we've built here. The models we've built are actually in use. So the AKI is actually being built right now as a BPA for our burn surgery colleagues, because it's in its third stage, and we've done the multi-center studies on it too. And then this one here, it's actually within the medical school administration where they're using it internally to see, assessing students to see if they need to intervene and help out students, about 1.5 years in it, the early ones to identify students, and then 6 to 7 months before the USMLE to see if they need to do anything or help out the students in any way. So again, models that are actually used in real world applications. Ultimately, this is how MILO works. So if you came up to me, I've been doing machine learning for a couple of decades, and so obviously I'm going to have my own biases. So if you came up to me with your data set and you said, "Here's my data set. What do you think, Hooman? What should I do?" I would have my own biases. I may say, "Oh, the best thing for your data set is a neural network." If you go to another machine learning expert in Minnesota, they may say, "Oh no, the best thing for you would be a random forest," and another person in another center may say, "No, we should do a parametric, approach and do logistic regression." And so who knows who's right? So there's obviously all these biases involved. So instead of a machine learning expert or a machine learning expert group deciding what's best for your data set, we let your data set decide what's best for it through MILO. So MILO becomes a matchmaker. And it becomes a matchmaker while following the industry's best practices, the CRISP-DM that I mentioned earlier. And actually, we have an enhanced version of CRISP-DM, and we've made it harder because we're dealing with healthcare data. So we actually, and within our study designs, we require a secondary data set regardless. So you can't do MILO with just one data set. So if you only have one data set, you have to heuristically build two if you want to do MILO. So exactly how does this platform work? This is your typical approach, and this is kind of like the more enhanced version of what I showed you earlier with the CRISP-DM, the study design within machine learning. So we follow the same approach, but everything in the yellow that you see here, that's typically done by different groups or even within the same group, different platforms. In MILO, it's all one. So everything is within MILO's pipeline. So everything in the yellow is all automated. The only thing that the user needs to do is they need to bring in their data sets. So we require 2 data sets to be brought in, one that actually gets split into training and testing to build and validate the models. And then the second one that actually in the red that basically says these models that are now validated, how well are they performing in real life with prevalence dependent data set. And then if they're delivering properly, then they can be deployed. So we even let the users deploy the models and start testing them either individually or embedded within their LIS or even within their clinical trial as a batch mode, whatever else that they're looking to do. Ultimately, it allows within this automated platform, you basically can take care of missing data. We can scale the data and then you can also find out which features are the best because maybe not all the features are the best for making the best model. So maybe some features hurt the model. So this will find out what unsupervised platforms embedded. We'll find out what's best before you actually feed it into the supervised platforms that build the models. And then the supervised platforms use most of the commonly used algorithms, including our own neural network. And so 7 of the most commonly used supervised machine learning platforms in the world are embedded within our platform. And ultimately, you build the model, validate it, and then the ultimate test is that secondary data set, which says, okay, now that you've built those models and validated, how well do they really do on the real data set that's based on the prevalence? And then if you're happy now with the performance, and depends to whatever you're looking for, so you may want to be looking at the best F1 score, or best accuracy, or best sensitivity, whatever that's meeting your needs. And if you're happy with that, then you can actually deploy it. If you're not happy, then you can rebuild new ones. And then when you deploy it, you can start seeing it. So that's basically a one-stop shop to be able to build models and start using them. And exactly, can it find models that were basically extensively studied? Here's a great example of it. This was our sepsis model, a very large study, about 50,000 models built. Took us about 4 months to do this study, and we found that needle in the haystack for sepsis, where within burns patients, we found a fantastic model of how well it was performing. And our main question was, can MILO find the same thing? And the answer was MILO did. So MILO found it, but instead of 4 months, it did it in less than a day, which was the biggest thing for us. But it found that same one that we found here in here. But obviously, it had to build 6 times the number of models. But because it had built that extra number of models, it has additional optimized models embedded. So guess what? It actually found additional models that outperformed the original non-automated approach. And so that was exciting because we actually have repeated this with the other test sets too and the other studies, and we're seeing the same thing. So, and it's a common sense thing. If you have increased number of optimized models, and obviously a human can't be evaluating this many models, but a machine can, especially if it's got the right embedded algorithms within it. So obviously the approach is very simple, is that you build hundreds of thousands of optimized models, and most importantly, it should be following machine learning best practices as we have and others have published on. So a quick demo in terms of how MILO works. So imagine you want to predict sepsis as your target. And so everything in the grayed out area, MILO will do automatically for you. And you want to basically just bring in your data set. So this was our clinical trial for sepsis. And we have about 250 positive cases. The ones are positive and zeros are negative. And then the columns in the blue are your features. So if the ventilation status, white blood cell count, platelet, BUN, creatinine, MOD score. So all these different clinical and laboratory values that were collected. And so you're going to feed this into MILO, and MILO is going to learn from this and say, okay, what combination of these are best suited for the negative sepsis cases, and what combination of these are best suited for the positive sepsis cases. And in terms of its process within MILO, is a super simple approach. We have a 4-step approach, and the first step is selecting the data, and that basically you bring in the 2 data sets that I was mentioning, and I'll show you that in a second. The second step, and you select your target. The second step is you actually evaluate what was ingested within MILO so that you can basically see if there's any weirdness to the data or if the stuff were uploaded properly. And so that's, standard practice for best practices within machine learning before you actually do the modeling. And then the third step, which is the brain, is training the model. And that's where the brain of MILO is. And so that's what I'll show you, where that's how you build hundreds of thousands of models by having thousands of pipelines. And then finally, those hundreds of thousands of models that are produced, they basically give you the final results of each model in terms of how they've performed. And then you as the user can decide, is that the performance measure that you were looking for, and does it meet your needs? And if it is, then you can start deploying it and start testing it further. So in terms of how it actually works, if you can attach a file into an email, you can attach it into MILO. It's that simple. So you just press the select training data, and then you can just attach the CSV Excel file into the thing, and puts a check mark next to it, says you're good to go. Now you put in the secondary data set, the one that was the prevalence. In this case here, the ones that they collected afterwards are retrospective, and this was the prospective ones. These were patients where 20% of them, or about 20% of them, had positive cases, and 80% of them were negative for sepsis, but obviously with the same feature sets that were collected. And so you just upload them the same way as we did earlier with a CSV Excel file, and you basically upload it, and now you choose the target. And obviously this is an optimized binary classification model, so your target is it sepsis or is it not sepsis? So you just basically click the sepsis, and now you're ready to go, and you can press the next button and you move on. So now in terms of how it works in real life, I think the video shows it best. So you click the training data, attach the training initial validation. So this builds the models and initially validates them. Then you obviously want to see how well do they do in real life stuff. You put in the secondary data set, so that puts it there and says check is in. Now you check out what column headers you have, and obviously the column header with the target is sepsis. And now you go to next, and now you evaluate the 2 different data sets that were ingested in MILO. So the training initial validation on the left, generalization to the right. The initial training, initial validation was about 50-50, half of them positive, half of them negative. The one on the right was 20% positive, 80% negative. Now the brain of it is here where you're building the pipelines. A typical machine learning study uses 1, if you're a bigger group, 10 pipelines. With this combination that I'm showing you here, which is our default, you can build about 2,000 pipelines, which is what we recommend doing. And then, but you can, let's say you're a machine learning expert, you can actually customize it the way you want it. So you can uncheck it, and for sake of time, I'm unchecking some of them so it doesn't take forever, because it usually takes 3-4 hours to run it. So this one is going to take a few hours to run, like an hour or so. But obviously, within this hour or so that this is going to run, this wheel of pipelines, which each spoke of the wheel is a specific pipeline that is actually running. It shows the algorithms that you can see, the neural network with different feature sets that were picked out, different scorers, different searchers, and then ultimately this is going to go on and keep on training. Obviously, it's going to take a few hours, so a little while later, when the wheel gets close to 100%, so it's not 99%, when it gets to 100%, it automatically throws the user into the results section, the 4th step. And then within the results section, it pops up by default, because most people are asking us for the top average sensitivity specificity with the highest sensitivity. But you as the user can choose whatever model performance you want, the ROC-AUC, accuracy, F1, the lowest prior score, whatever you want. And the top model that you see in gray correlates with the graphs that are on top. So it's ready for even publication purposes. It's fully transparent, so you can see exactly what you've run. You can see the details in terms of what you've built. So we built 129,000 models there, the 500 patients, so 250 positive, 250 negative, and then see the generalization test set and what kind of a statistical cross-validation you've done. But now you see, okay, I've built a model that is very good. It's got 100% sensitivity, 85% specificity, but it was with only half of the features that you basically put in. So I don't know exactly what those half of the features are. And most platforms, they're closed, where you can't see what is it that you're looking for. If you can see them, it'll be hard to see. And so within our platform is 100% open, where it's transparent. And what I mean by this is that if you want to see exactly what these were, because we're transparent, you can actually download that entire file here, this table, as an Excel file on your desktop and do additional testing. You can even rebuild models on your own platform. If you're in machine learning, you can even do them in your Jupyter notebook, rebuild the models. And we've done thousands of validations, so we're very comfortable with people kind of doing whatever they want with the data and even the results. But in this case here, the Excel file gives you a lot more granularity. So, you can see the confidence intervals with Copper-Pearson method embedded. You can see the true positive, true negative, false positive, false negative. So you can redo the stats if you want. You can see the hyperparameters, exactly what it is. But in this case here, I wanted to see what the selected features were, that 50%. So exactly what features were selected. So you can just open up that column and see exactly what those 50% of the features were. So respiratory rate, temperature, white blood cell, TCO2, those ended up being the best out of all the features that were selected. So now as the investigator, you know a lot more about which features were selected. So now if you're happy with that model, you can now actually start testing it live. You don't have to wait. So by pressing the green button, you actually can start testing it immediately. So obviously if I can do single testing or batch testing, and I'll show you the batch test in a second, but a single test is like if I put in some basic parameters for somebody who should have sepsis, let's see if they will basically show that they have sepsis or no sepsis. So somebody who should have sepsis, if you enter the values in there, or this could get auto-populated with an LIS too, and then once everything is in there, the predict button basically highlights it and you can click it and it will say, yeah, this is a positive patient for sepsis, 62% probability. And then, so it's a good enough model that you may, as an investigator, say, I want to move forward. But you may want to do a clinical trial and dealing with hundreds of cases, so you don't want to manually update them. So for those, we recommend just fixing the model, putting it on your homepage. So it's just naming it is that easy. And within a second, you've built your website with that model that's fixed. So now you don't have to retrain the model every time. The model is ready for you to test every time you want to do. In this case was a batch test. So if I want to do a self-batch test on that secondary data set and see what was it that missed and what was it that got right. And so you can just see how in a second you can actually see the prediction, and it pulls up another Excel file for you on your desktop. And you can see the last two columns, which was prediction and probability. This one had 80% negatives or zeros, and you can see some false positives in there. So as an investigator, you can dig into that and find out why was it called positive when it was really negative. And so again, a lot of transparency, and you as an investigator can kind of learn more from your data as you use the platform. And it's because the platform is made so that it makes your life easier, so you can do your studies better and ultimately find the best models that ends up being helpful for yourself and ultimately your patients that you're taking care of. So this is basically MILO in a nutshell. And in summary, it's super easy to use. No machine learning expertise is needed. No programming or software engineering expertise is needed. It's basically your machine learning and software engineering team at your fingertips. And it follows machine learning best practices and finds the best models and does it much faster than the non-automated approach. And most importantly, it's a validated platform especially in our world. And I want to thank a lot of our collaborators that are part of our group. And with that, I thank you for your attention. I'm happy to take questions. Thank you.
Any questions from the audience?
Leo Furt here.
Hi.
Thank you very much for this really stimulating talk. I wonder if you or anybody in the country has used MILO for COVID to maybe tell us which patients are going to really go down and have sort of premonitory lab data or other data that would allow us to say this person's going to really need aggressive care. We got to get on top of it very quickly.
Yeah, that's a great question. And we are actually. So the biggest challenge we have, unfortunately, I mean, it's kind of embarrassing to say as an American, I have to say that our data system in the US it actually lags behind some of the other places because not because we don't have better data structures. We have great data structures. We just don't share them. Everybody kind of, works in silo, and that has to do with HIPAA and other reasons. So the simple answer to your question is yes, we are. So we are building models that can predict, specifically that can predict who's going to go into the ICU, who's not going to go to the ICU. So that happens to be one of our big one. We actually have a grant from one of the WHO facilities, and it's a direct study with the government of Pakistan, where they're basically collecting the data the way we want them to, and we're basically doing exactly what you said, which is, can it be an ICU prediction versus not? Also within the University of California system, we've already built it, but we're doing the final validations of using the um-lmp data, which is the University of California-wide data of all the patients who had COVID and which ones went into the ICU, which ones did not went into the ICU. And then so using MILO to actually build who's going to be positive, who's going to be negative. So in short, yeah, we have 2 active studies on that right now, and a third one which is going through a grant, which is doing something semi-similar but with additional biomarkers, which means that can you use a biomarker profile, because we have a paper coming out with MILO on tuberculosis, and we've used serologic data on different antibody profiles and how the immune system profile could predict who's got active TB versus not. And we're using that same concept within this grant proposal to see if we can kind of do the same thing with COVID in terms of who's going to be the real aggressive ones and end up being in ICU, whatnot, and who's not. But that's a very good point. Absolutely, we're doing that. We're hoping that we could put these in more hands out there, because the ultimate thing is that because the thing that I've realized the most out of this whole situation with COVID is that, yeah, obviously our unpreparedness as a global community, there's no doubt there. But so hopefully that has, strengthened us and made us better in terms of being able to deal with this and future things. But most importantly, finding ways that we can incorporate tools for anyone within their medical center, because let's face it, we have to still abide by our own local rules. So having a data management system, or actually a predictive analytics system that's easy to use at individual sites makes a lot of sense to me, because even without COVID, let's say later on people want to use it for sepsis, maybe the sepsis in my community, those patients may behave differently than in your community because of antibiotic usage or change in environmental factors, and who knows, a bunch of different variables. So because of that, I think the future would be more individualized, platforms embedded with generalized models. So some models that would work for all med centers, regardless of what the disease is. But then probably the better models will be the ones that are targeted for individual institutions, or maybe individual regions or individual countries, that sort of thing. I hope that answered it.
Oh, yeah, wonderful answer. In your ICU studies, just a suggestion if you're not doing it, but it might be also good to see if you can predict who goes on ECMO. Right now, we have a handful of young men who are on ECMO in our shop, so it'd be nice to know.
Yeah, absolutely.
The next question I have, and then I'll stop, is how is MILO accessible? You've patented it. Is it been commercialized? Just how does one play with it?
Yeah, so that's a great question. I don't have any, I can't negotiate for MILO, because as a professor at the university, we give up our rights to the university. So that's something that the university does. To be very transparent, MILO has been licensed to companies and even universities. So even though it's only been 6-7 months, the minute after we presented it at the JP Morgan conference a few months back, all of a sudden a lot of people were interested in licensing it. So yeah, the University of California definitely has platforms that can give people to use. So I'm happy to connect you with the people who do that. So if you have an interest, I believe they do non-exclusive licensing platform
Sure.
where you could
Yeah.
use it in your own institution and whatnot.
Yeah, I mean, thank you for that, because I can see tremendous use for our whole practice. Where the major cause of deaths in our institution is sepsis, and we have the data that we're looking at, but I got to believe there are other biomarkers that could give you earlier signs and signals about what's going on.
100%.
So I will follow up with you. Thank you.
Oh, terrific. Yeah, please email me. I'm happy to connect you to the right people.
Okay, and Dr. Lee has a question. Danny, go ahead.
Hi, I just actually have a follow-up question. So how big a data set need to be in order to use MILO?
That's a great question. So the answer to your question is, I don't know. I don't want to act like I know the answer to that. But I can tell you from my experience what the range was. I hope that helps. So I think the size of your, obviously, let's face it, one of the reasons MILO is popular is because we've optimized it with not large data sets. So because most of the stuff that we're dealing with in medicine and pathology and laboratory medicine and medicine in general is, studies that have a few hundred patients or maybe a few thousand if you're a bigger study. But it's not like, a Google non-medical study where you're dealing with millions of, populations or millions of subjects. So because of that, it's optimized on smaller to intermediate sized data sets. That being said, in terms of how small can you go, I definitely do not recommend doing it with less than 100. Although that being said, from a transparency standpoint, when you do have like an incredibly powerful biomarker, you could probably still get reasonable results with something like NGAL, even if you are slightly below 100. But I would typically say your typical study sets should be, at least a few hundred, so that you can at least, even if you don't, most people don't have both of the data sets. So if you're heuristically building both of the data sets, that you're starting at least with a few hundred, cases to kind of get going. I hope that answered it. I know it was kind of vague, but obviously if you have a lot of data, like, we have studies that is run with, thousands and thousands of data, it does fantastic with those. But I think any platform can do fantastic with those too. There are not that many AutoML platforms out there, but there are some. But the ones that I'm showing you in terms of the validations were done on data sets that were within, a few hundred to few thousand. Did that answer?
Yeah, thank you. Because I actually, like Leo mentioned that, there's a lot of interest for COVID. So I actually have just recently have a COVID data set that I'd be very interested in, using MILO for. But so it sounds like, it will take some, legal work or fee that in order to have access to this.
Yeah, 100%. And I have to say, I mean, obviously, I'm friends with some of your faculty, and some of your deans actually are my boss's friends. I believe your past dean was going to come up and give a talk to us, Dr. Powell. But so we have like good connection with Minnesota. So if there's ways that I can actually help you with studies, especially COVID, I mean, I'm willing to do free stuff for COVID. So if there's ways that, you have something and you would want us to help you from our standpoint, obviously we'll have to go through the whole, kind of making sure that I'm on the IRB and stuff like that. But we can definitely do stuff, collaborative stuff together too. So you don't have to necessarily get MILO. We can do the MILO stuff for you, because my team is, kind of primed up, and it'll be hard to kind of have a big team. It will take a few years to kind of build it up. But just let me know. I'm happy to help.
Well, thank you.
Sure.
This is Tony. Can I have a quick question? That was a fantastic presentation. Thank you very much. My question is, I got two questions. The first one is to do with the Burns study and the AKI. You said that this was creatinine measured at admission.
Yeah.
NGAL. Did you include other things like age and gender and ethnicity? Is that part of the model too?
Yeah, so that was a separate study that they published. I was not on that study. So they did a statistical modeling approach, non-ML, and that they did based on what you just said, which is a good point, which was on age and a lot of other parameters, also burn size and this and that. I mean, all sorts of the things. And with ours, they wanted to see, initially it was, just to be frank about it, initially it came up to me as a joke by one of my closest friends, Nam Tran. And he basically said, let me see if you can do this with just these parameters alone. And when he gave it and he saw the results, he's like, no, let's just keep it that simple. And the reason, but I agree with you. I think if you added these additional parameters, you may even enhance it further. But we're not sure. It may enhance it, it may not enhance it. But we never tested that. But that's something we are doing on our future ones. So as we're studying these.
And then if I could ask a quick question about MILO, is it more than just the individual routines like random forest and K nearest neighbors, all of which are available in, say, R?
Yeah.
Are there additional modeling factors or algorithms in there beyond the standard ones?
Yeah, so that's a great question. So the gold standard for non-image machine learning is, as you know, it's through scikit-learn. So our platform actually emulates scikit-learn. So we didn't want to, quite frankly, we wanted to follow the gold standard, an international gold standard. So and because that's validated across the world, and I'm part of that community. So it's like, and we use it all the time. And so we wanted to use the same algorithms that were embedded within it, but use our version of how to optimize the hyperparameter windows. So within each one of these algorithms, in order to find the best bias variance trade-off point, there is these other parameters, which we call hyperparameters, which nobody really can guess. They're not, these are things you just have to empirically find. And in order for you to empirically find them, you have to build search tools and kind of these mathematical window search tools ultimately find where is the best window for a given data set in terms of where its optimized hyperparameters are within each one of the data sets for, let's say, random forest or for a neural network or even logistic regression. And then once it finds these hyperparameters, it then tunes that model so that then it basically ends up being your best model. So our platform uses actually our IP is around the combination of our hyperparameter searches, which is a combination of our own custom grid and multiple randoms, along with our own version of different unsupervised feature selectors. So that combination gives us the kind of the uniqueness of it, of how it came about.
Okay, thank you.
I hope that answered it. Sure,
Yeah,
sure.
Thank you.
Thanks.
Okay, on behalf of the department and Dr. Williams, thank you for joining us this morning, Dr. Rashidi.
Thank you so much.
We'll be on again next week with Dr. Megan Hupp as our guest speaker. I'd like to thank you all, and I will see you next week.